So we're back to the topic of confidence intervals, this time for a difference in proportions. So for starters, what are the conditions? And these are things you've seen before. Randomness, meaning the data that we're going to make inferences with, it comes from a random sample or a randomized experiment. And then we know we need independence, which if we're sampling without replacement, we need to use the 10% condition. If it's just a randomized experiment, or for some reason you're sampling with replacement, you wouldn't need the 10% condition, right? Things would already be independent. And then for normality, which we're familiar with, but we need to keep this for both samples. So the large counts condition, which was 10 successes, 10 failures, that has to work for both samples, the one that P1 came from and the one that P2 came from. So that has to happen for both samples. So we're making a two-sample Z interval for the difference in proportions: random, independent, and normality. The three conditions we've come to know and love in AP Stats. The next part here says, what is the standard error of P hat 1 minus P hat 2? And how is it different than the standard deviation of P hat 1 minus P hat 2? Because we looked at the standard deviation in the last notes. So the notation here, standard error, is capital SE, and then the subscript we have P hat 1 minus P hat 2. That's the notation. And then you'll notice there's a giant square root, N1 over here, plus N2 over here. And we still use P1, 1 minus P1, P2, 1 minus P2. Now we just have hats on each one. So very similar to actually the standard deviation that we looked at in the first notes. The only difference now is the standard error uses the sample data. It uses P hats instead of just the P's. Keep in mind the hat, that implies that it came from sample data. Right? So people going out into the world and acquiring data, that's what the hat means, sample data. And then just lowercase p by itself, if it's a p without the hat, that refers to like the true population proportion. So the standard error, that uses p hats, the sample data. The standard deviation, yesterday, that's the one that used just P1, P2 without the hat. So what does the standard error thing measure? Well, it measures how far the difference in the sample proportions, which is P hat 1 minus P hat 2, right? That's the difference in our sample proportions. So it measures how far that difference typically falls from the true difference in proportions. So what would the true P1 minus P2 be? So similar definition for standard error that we're used to. Now it's just how far that difference for the sample data typically falls from the true difference. And this is what we're going to use to help build our confidence interval. So what is the formula for a two-sample Z interval for the difference in these proportions, P1 minus P2? Well, you start with your sample data, right? You have the first proportion minus the second proportion. So P hat 1 minus P hat 2. Then plus minus, that should look familiar. And this is a Z interval, so we got a Z star, which is our critical value, by the way. We call that a critical value, times that standard error piece. So the square root with all the P hats underneath it for the first sample and the second sample. So this should look somewhat familiar. Right? We have sample data plus minus a critical value times the standard deviation. That's how we build our confidence interval. Is it on the formula sheet? No, we wish it was, right? But it's not. The formula sheet has a really general formula for confidence intervals. It doesn't have this. So let's go to the gun control example here. It says, have opinions changed about gun control? Gallup regularly asks random samples of U.S. adults their opinion on a variety of issues. In a poll of 1,011 U.S. adults in January 2013, 38% responded that they were dissatisfied with the nation's gun laws and policies and want them to be stricter. All right, so that was from 2013. In a similar poll of 1,011 adults in January 2012, only 25% agreed with this statement. So part A asks us to explain why we should use a confidence interval to estimate the change in opinion, rather than just saying that the percent increased by 13 percentage points. So why can't we just say that that 13 percentage point increase represents all U.S. adults in America? Well, because sampling variability. So because of sampling variability among different samples of U.S. adults. So even if they were randomly selected, a sample of 1,011 U.S. adults versus another sample of 1,011 U.S. adults, they're going to have different results, which means the observed difference, that 13%, is unlikely to be truly correct, right? Or exactly correct. So just because we have one single proportion compared to another single proportion, think about the sampling variability. There's all sorts of different random samples of 1,000 adults that could have been chosen. So those results could have varied quite a bit. So to account for that variability, we're going to build a confidence interval. So instead of letting that 13 percentage point number represent the two populations of adults, we're going to build a confidence interval so we have this interval of plausible values. We'll use that 13 percentage points, but we'll allow for some variability, some plus minus to occur. And that's really what confidence intervals do. They allow us to account for some sampling variability, right? So we can reach out a few standard deviations above and a few standard deviations below our sample data. Okay, so part B, it says use the results of these polls to construct and interpret a 90% confidence interval for the change in the proportion of U.S. adults who would agree with the statement about gun laws. Okay, so this is a 4-part grading rubric. We start with the state step. So what do we want to do? We want to estimate, or you could say we want to construct an interval. I like estimate because it's shorter. We want to estimate with 90% confidence the true difference of P1 minus P2. And again, I like that word estimate. That implies that we're going to build an interval of plausible values. We're going to make an estimate for the true difference here. The only thing that really we're lacking right now is what the heck is P1 and what the heck is P2? And it definitely matters what order we're subtracting them in. So let's give it some context here. So we can say where P1 and P2 would be the true population proportions of dissatisfied U.S. adults in 2013 and 2012, respectively. And I put just dissatisfied in quotes because I didn't want to write the whole statement that they used in the question. Do P1 minus P2, or the one from 2013 minus the one from 2012, which 2013, if we just go back here, that was 0.38 minus the 2012, which was 0.25. So that's where they got 0.13, the 13 percentage points. So we just have to keep the order straight here. It was 0.38 minus 0.25. So that'd be the 2013 version minus the 2012 version. So the state step's good. We said what level of confidence we're using. We noted the parameters, right? The true difference, P1 minus P2. And we defined what P1 and P2 were in context. There's 3 points. So for the plan step, we need to name the inference method first. So if conditions are met, we'll construct a 2-proportion Z interval. And that's what we're going to use to try to capture that true difference for P1 minus P2. So there's another point right there. Name the inference method. I know we did hypothesis tests last chapter. Now we're starting off with intervals again. This is a 2-proportion Z interval for the difference in proportions. So randomness, I believe it said in the problem, right? Both samples were randomly selected. Check mark, that one's good. And independence, this should actually be an easy one, right? I assume they didn't sample with replacement, but the sample size, 1,011, that's well below 10% of all U.S. adults, right? So the 10% condition is clear. So we are definitely safe there. 1,011 adults is definitely below 10% of the population size for all U.S. adults. So random's good, independence good. The last thing we have to do is meet normality. And we have to have 10 successes and 10 failures at least for both samples. So let's start with the first one, N1 and P hat 1. So the sample size was 1,011, and then P hat 1, proportion of successes, we'd say is 0.38, which 384.18 is definitely at least 10, check mark. So there's our 10 successes, we'll call it. And then we do N1, 1 minus P hat 1. Do we have at least 10 failures? Yeah, we definitely do, right? Sample size is 1,011. If you do 1 minus 0.38, now you get 0.62. So 626.82 is bigger than 10, check mark. If you're curious why these are rounded, well, it seems like the proportions were probably rounded to two decimal places. So when they said 38%, that was probably 384 people. And then 62% would have probably been 623 people. It was just the proportions themselves that were rounded. Okay, we got to do this for the other sample as well. So for N2 and P hat 2, well, the sample size is still 1,011. And then P hat 2 would have been 0.25. So that puts us at 252.75, which is at least 10. So that one's all good. So at least 10 successes for the second sample, and then for the failures, N2, 1 minus P hat 2. So if 0.25 was P hat, then 1 minus P hat would be 0.75, which puts us well above 10 successes. So we are actually good. All four of these values are at least 10. So we can say because they're all at least 10, the large counts condition is met. Check mark. We are good for normality. So the math behind it's pretty simple, but you still have to go through and check it for each one if you want credit. You can't just say because all of these are at least 10, right? That won't work. You have to actually show each one, illustrate each one if you want the credit. Trust me, I'm not just writing this stuff out for my health. All right, so we're good with the state step, we're good with the plain step. It's time for the do step. So let's start. We're going to build this 90% confidence interval. So we do the difference in the two proportions, P hat 1 minus P hat 2, plus or minus our Z star critical value, times that big square root thing, the standard error for the difference. Okay, and if we can at least set this up correctly and then plug in the right values, that should earn us some points. So we know what P hat 1 is, 0.38. P hat 2 is 0.25. We should note that the critical value Z star here for 90%, that's 1.645. And if you forgot where to find those, you can always use inverse norm and use the tail probabilities, or you can look at the very bottom row of a T-chart, the infinity row. That'll give you the Z stars for our confidence intervals. Or you might have remembered the big ones, right? 1.645 is the Z star for 90% confidence. And then let's go ahead and set up the square root here. So 1,011, sample size was the same for the first sample and the second sample. And then P hat 1, 0.38, 1 minus that is 0.62. P hat 2, 0.25, 1 minus that, 0.75. Okay, so the difference in our sample proportions is 0.13. That's what they were talking about at the very beginning of the problem. And then if we multiply 1.645 times this big square root thing, we should be looking at about 0.03365. That's our margin of error. Right, so there's our sample data, our sample difference in proportions, plus minus our margin of error. So we add it to 0.13 to get our upper bound for our interval, and then we subtract it to get the lower bound which gives us from about 0.096 up to about 0.16365. So from somewhere around 9 percentage points up to somewhere around 16 percentage points. Okay, and there is a calculator command to get past plugging in all these numbers to your calculator, right? So there is definitely a calculator command, and we'll get to that in just a second. The conclude step, and hopefully you're used to this from Chapter 8. We are 90% confident that the interval from lower bound to upper bound what does that interval do? What do we build it to do? Well, hopefully, we don't know this for sure, right? We'll never be able to know this for sure, but hopefully it captures the true difference in the proportion of dissatisfied U.S. adults from 2012 to 2013. We did that a bunch in Chapter 8, so I'm hoping you recognize that and are comfortable with that as far as using context and setting that one up. And the word capture, I like that word. So that's it. We built the interval, we concluded. Now part C says, based on the interval, is there convincing evidence that the opinions about gun control have actually changed? I know they were different in 2013 and 2012. In fact, the dissatisfied percentage was 13% higher in 2013. So based on the interval, do we have convincing evidence that the opinions about gun control have changed? So maybe that 13% increase in 2013 was just due to sampling variability, right? Just a random chance you got a different sample of 1,000 adults, and just random chance that they answered yes more often. Okay, so through our interval, though, there's a certain value that we're not seeing, right? Think about if they hadn't changed. What if 2012 and 2013, what if the true proportion really was the same? Well, if they were the same, then when you subtracted them, you'd get 0. If you notice, 0 is not on our interval. All of our values are above 0. So that means we could say with confidence that, yeah, opinions have changed. We wouldn't even consider 0, like no difference, a plausible value. And I keep pointing down here because, like, if there was a number line, 0 would be down here somewhere. So that's the key here. Look for the number 0. And since 0 is not included on our interval, well, 0 would mean, like, hey, there's a chance that they're still the same, right? You subtract them, the same number, you get 0. So if 0 are on there, there's a chance it's still the same. But 0 is not on ours. So that means we do have convincing evidence, right? We've got convincing evidence that the opinions have changed. Basically, we can say the proportions increased, right? I know the sample proportion, the difference was 0.13. So we're not saying it's that value for sure, but we're 90% confident that the true difference is somewhere between 0.096 and 0.163. And the fact that 0 is not on there at all is what makes us confident that they've definitely changed, right? They've increased in 2013. So just a really important side note here. 0, if you saw 0 on the interval, that would indicate that there might be no difference if you did P1 minus P2. We didn't get 0, though. Okay, last note here for these. Can you use your calculator for the do step? Yes, please do. You saw how many things you could mess up with the plus, minus, and the square root. So it's under stat, tests. There's a bunch of different tests to choose from, but for this type, it would be 2 prop z int, 2 proportion z interval. Are there any drawbacks? Just keep in mind that you should use integers for the inputs, and I'll show you that here. So if I click Stat, and I go to Tests, and I want 2 prop z interval. All right, there it is, 2 prop z interval. I'm going to enter, and it doesn't say anything about p hats. It says x1 and n1, and and then x2 and n2. So you need to think about the fractions that you would use to make like p hat 1 and the fraction you would use to make p hat 2. For example, p hat 1 was 0.38. So the proportion of successes was 0.38. That means we had 384 out of 1,011 for P1. And then for P2, we had 253 out of 1,011. Where am I getting those numbers from? Well, think about when we calculated in the normality condition, right? Number of successes for P1 and the number of successes from P2. Okay, then I'm just going to set my confidence level to 90%, 0.9. Go ahead and hit calculate. There's my P hat 1, there's my P hat 2, and there is my confidence interval. So, yes, you can absolutely use a calculator. I like when kids use their calculator just to be sure to identify or label all the inputs, and especially the critical value, like we did in the example earlier. And by that, I mean, at least we were able to set up the plus-minus expression here. And then now you can clearly see that I know what P hat 1 is, and P hat 2, I know what that is. I know what the Z star is. They're lined up. But from there on out, you can at least just use 2 prop Z int in your calculator to get this. All right, so there you have it, your first experience with a 2 proportion Z interval. That is all for these notes. I'll see you in class.